Hello. So I'm going to talk about a simple concept, what is called measures of central tendency. This is divided into two parts. The first part talking about the means, and before that let me introduce what is a central tendency. See, the whole purpose of statistical treatment of any data is to summarize and describe the data meaningfully and adequately. So, in this process, we can't describe the sets of observations meaningfully simply by looking at the values of all individual measurements. You need to summarize a set of observations by way of some procedure, and the most common one, which you already know from your school days onwards, is what is called frequency tables. So these frequency tables, what do you do really? You really make the entire data into some meaningful classes or nearby values, group them and call it a class interval. And in this process, you could reduce it into a few meaningful categories, frequency distributions, but they do not give us a single index or one value which is typical for the entire data set. So, but that one single value, typical value, is required because it's easy to summarize with one value, and also if you want to compare two or three more similar data sets, is easy to compare with a single summarized value. So, for example, if you have a data, let's say the height of school going children, if you have a sample of 100 in children or 200 children, it's okay to have the data, but to make things simpler, to make others understand, and for your own understanding, you might like to ask yourself, what is the center or middle of the data set around which other observations are lying? Or you can also ask, what are different locations in the data set that divide total data into certain proportions? For example, you can summarize the data by saying 50% are above a certain value and 50% are below the same the value. So what we call, these are measures of location. These indices are called measures of central tendency and location, and somebody else will be talking location. I am going to talk of the first three: arithmetic mean, geometric mean, and harmonic mean. The other two central tendency measures, median and mode, and the extension of median into other place measures of location like quartiles, quintiles, tertiles, and so on and so forth, will be talked by somebody else. Let's take the first one. What is arithmetic mean, or more commonly simply mean? Arithmetic mean is the average value of the variable. It is obtained by taking sum of all observations and dividing it by the number of observations. If we have 10 gestational ages or gestational ages of 10 newborns, which are shown like this, 36, 38 to 41. This is what we call the raw data, and by looking at this, we don't have the total picture of the distribution, or what is a typical value for the gestational age of all children born in a particular clinic. At best, you can have a look at the data, a quick eyeballing the data, and may be able to guess that minimum is about 32 and maximum is 42. So apart from that, you cannot really make meaningful inferences or conclusions about the data that is in this raw format. Even eyeballing the data and having a fair idea about the minimum and maximum type things may not be possible if you have the huge data. Let's say instead of 10 newborns, you have 4,000 newborns or 6,000 newborns. Then eyeballing may not be even helpful to understand what is the possible range, minimum, maximum type of things. So you need to summarize this raw data into an index that can be easily understood, interpreted, and maybe even useful to compare with other similar data from another hospital or another place. So mean gestational age of these 10 newborns is, first, as we know, you add up, get the sum of these 10 observations, which in this example is 380, because there are 10 observations divided by 10 and it works out to be 38 weeks. If you want to show the mean as a formula or notation wise, you indicate generally mean as x bar and summation, this is a Greek symbol, summation from I equal to 1 to n. The I is, even the first observation, I is 1, last observation, I is 10. So in a generic term, summation I equal to 1 to n xi. I, first one is, when we talk about first observation, I is 1, second one, I is 2, like that. And then add up, divided by n. So this is how we show the formula of calculation of. But earlier we showed, what we discussed in the earlier example is the raw data. That is 10 observations as it is, you have the actual data that you collected, how to calculate the mean. But sometimes you can have a group data which is a frequency distribution like the one I am showing here. It could be systolic BP 90 to 99. There are 3 persons, 100 to 109, 5, and like that there are total 68. But don't get confused here, or be clear what happens if a person has 99.5 or 99.9. You mean we don't get the impression that we have excluded or we have not considered. It's not correct. It is for convenience sake we are showing 90 to 99, but in reality anybody up to 100, 90 to 100, but not 100, will be considered in this interval. The moment it is 100, he or she will go into the next interval. Similarly, here in next interval, the 100 to 109 we are showing, but actually what we mean, 109.99999. Any number of nines, as many as you like, you can put. But the moment is 110, he or she will go to the next interval. So coming back, if you have the frequency distribution like this, how to calculate the mean? The same formula of earlier what we discussed with raw data. Instead of the each xi, you multiply by the frequency. That is what we have. But each xi, what will you take? 90 to 99 are 3 persons. So you need if you have the raw data, you know each individual who is, somebody may be 91, somebody may be 97, another may be 99. But we don't have. Now it is grouped data. So what we presume, these 3 observations are likely to be close to the midpoint of this interval. What is the midpoint of this interval? 90 to 100. So 95 midpoint. And now 3 persons, each is likely to be close to 95. So the sum is 3 into 95, 285. Like that for all the intervals you calculate and you get a sum of 9220. And since there are 68 observations, you can divide it by 68. 9220 divided by 68, which is equal to 135 mm per Hg. So this is how you calculate mean for in a group data. Here you should notice, as I already mentioned, that we replaced a single value for all the values in the same class interval. 5 individuals falling in 100 to 109 or 109.999, we represented each one by 105, the midpoint of this interval. This may be correct, may not be correct, depending on your sample size and how extreme your data type of things. But in the long run, it is likely to be, if your sample size is large and data is following a normal distribution, then we are pretty very close to the truth that these people, 5 persons falling in this interval, are close to 105. But But you must remember that we may not be exact, in the sense, if you have the 68 observations, actual raw data, what you get the mean may be slightly different from what you get a mean from this group data. But because you wanted to make the calculation simpler, this is the price we had to pay. So that's how we calculate the mean, arithmetic mean from a group data. Now, there is another concept, not concept, I would say, the ease to make the calculations, especially if you are doing manual calculation. Instead of working with bulky big numbers, you can use a concept called change the origin. But what the effect of such change of origin? Let's take these concepts, discuss these concepts through a numerical example. Suppose you have 3 observations, 5, 10 and 15. The total works out to be 30, and divided by 3, the mean is 10. So far so good. Mean of observations now, suppose these numbers are too big. You think they are big, you can simply subtract 5 from each observation, or any number from each observation for your whatever you like. Here, because 5 seems to be common, I am taking 5. So if you subtract 5 from each, now that means original origin is 0. Now I am making my origin as 5. So my 3 numbers are now 5 minus 5, 0, 10 minus 5, 5, 15 minus 5, 10. So the sum is 15, again divided by 3, so mean is 5. This is the average or arithmetic mean of the numbers whose origin has been changed from 0 to 5. But we want the answer for the original data. So mean of original values will be the scale what you changed, 0 to what you have changed, that is 5, plus mean of the numbers with changed origin. So 5 plus 5, 10, which is equivalent to the one that we calculated without any change of the origin. Similarly, there is another useful technique. We can change the scale. What happens if you change the scale? Again, let's come back to the same example. You have 3 observations, 5, 10, 15. Total is 30 divided by 3, mean is 10. So now you change the scale. So divide by each observation by 5. So when you divide each observation by 5, you have numbers 1, 2 and 15 by 5, that is 3. So the mean is 2. So this is the mean of scale changed observations. So if you want the mean of original values, what is the scale that you changed? Multiply it with the mean that you got for the scale changed values. So here it works out. 5 is the scale that our new scale we got, and multiply by the mean of the scale change numbers, 5 into 2, 10. Again, as I said, change of origin and scale are very helpful to enhance the computational ease. This is more so if you have to do manual calculation as part of an academic exercise. These days computers are there, they will calculate everything for us. So you need not really worry about these change of origin and scale concepts. But to understand, as I said, if you have to do as an academic exercise, these are very helpful. Now, what are the advantages and disadvantages of this arithmetic mean? First of all, it takes into account all the observations. That's a very good property. It considers all the observations. Not only that, it considers the actual magnitude of each observation into account. This is also very important. And one good, nice property of arithmetic mean is it is amenable for mathematical treatment. What we mean by mathematical treatment is we know how it behaves in the long run, or its distribution, statistical distribution of an arithmetic mean. And also, if you have, let's say, subgroups, you have the mean of males, mean of females, then you can combine and have a grand mean, combined mean, we can calculate. That is what the property or mathematical treatment property, nice property of the arithmetic mean. One limitation is it's sensitive to extreme values in the data set. Any extreme value will pull the mean towards it. If you have very high values, 2, 3 high values, mean is inflated or pulled towards that high values. Or vice versa. If you have very few, some very small values, mean is pulled towards the low values. This is how I can tell you to make you understand. Let's say if you talk of an average income of an Indian, including persons like Adanis, Ambanis, who are hardly maybe less than 0.001% of the community, your mean is likely to be very high. But if you exclude those very small proportion of the community population, the reality is entirely different. That's what we mean by the mean. Arithmetic mean is sensitive to extreme values. And another limitation is you cannot compute arithmetic mean if you have a group distribution, but the class interval, open-ended class intervals, especially the last one. Remember the example that we talked about, it is 170 to 180. Suppose I don't know the upper limit, it is 170 plus. Then I don't know which value to plug in as the midpoint. Thereby, I cannot calculate the arithmetic mean. Okay, we will talk about geometric mean, which is another index which will convey the central tendency. If a variable can take only non-zero values, this is very important, non-zero values and positive values varying over wide range, what happens? The distribution will be skewed naturally because it varies a wide range. So it will be skewed and the variation will be high. For example, serum cytokine values, mean will be about 500, standard deviation will be about 700 or 800. That type of scenario you come across in this type parameters. So what happens is, in such scenario, arithmetic mean would not be an appropriate measure to convey the central tendency. So what we do, transform the observations into logarithms and calculate the arithmetic mean of the transformed values. Log transformation, how it helps? It reduces the skew-ness in the data. Skew-ness is another concept which I am sure you must have read in your in +2 or in undergraduation, first year, second year biology or statistics classes. Skew-ness is how much asymmetry is there in the data distribution. If it is a perfect bell, it is a symmetric data. But if it is not perfect, one side the tails are prolonged, then it is what we call the skew-ness. So log transformation reduces the skew-ness in the data distribution and makes it closer to the normal distribution. In a logarithmic scale, the distance between any pair of observations will be same if their ratios are equal, not the differences. If the ratios are equal, the distance between any pair of observations will be same. To tell you in a more descriptive way, the distance between 10 and 100 will be same as that between 1 and 10 or 2 and 20, because the ratio between 10 and 100, 100 by 10 is 10, 10 by 1 is 10, 20 by 2 is 10, and so the distance between any pair of observations is same if the ratios are equal. Similarly, the difference between 100 and 1000 is same as 10,000 and 100,000. Geometric mean is calculated as the nth root of the product of n observations. it is calculated as the nth root of the product of n observations. N is the sample size. Notationally, you can indicate as GM equal to nth root of x1 multiplied by x2 multiplied by xi multiplied by xn. So, and that is in a simpler product of I varying from 1 to n, and this product to the root or the power 1 by n. So this is how the GM formula is shown. And if you have an example data like 20, 5 and 10, the three values of a variable, the geometric mean of these three observations will be cube root of the product of 20, 5 and 10. If you multiply 20 into 500, 100 into 10, 1000, the cubed root. So to the power 1 by 3 is 10. This is how you calculate geometric mean. It can also be defined as arithmetic mean of the values taken on a logarithmic scale. Since you work on logarithms, you need to take antilog of the mean to get back the mean in original units. You want to show, suppose, geometric mean, if you call x as arithmetic mean of log values, take log with base 10, log values xi, and then sum up divided by n, that is the arithmetic mean of the values on transformed into log values. Geometric mean is antilog of this x. If you have 20, 5 and 10 as three values of a variable, log 20 is 1.3010, log 5 is 0.6989 and log 10 is 1, total is 3.0. So arithmetic mean of these three observations on log scale is 3 by 3, that is 1, and geometric mean is antilog of 1 or 10 to the power 1, which is equal to 10, as we saw in the earlier calculation of using the cube root. So geometric mean can be calculated as the product of n observations and taking the nth root, or arithmetic mean of the n observations taken on a log scale, and at the end you take the antilog to get the mean in original units. Let's see another example of geometric mean calculation. To be current, let us take the number of COVID cases seen in the country. This is on January 1st of 2022. We had 3,48,61,579 cases, which increased to 3,57,07,727 cases on January 10th. So if you see the increase, this is from first to second, there was an increase of 0.08%. And when you take on third, it was an increase of 0.18% from first. And like that, you have on 6th, it was 0.71% increase from 1st of Jan. And on 10th, it was 10th of Jan, 2.43% increase from the numbers that we saw on January 1st. Now, this increase, I rounded off. In fact, if you want to be accurate, you need to take more decimals. But I just rounded off percentage increase up to 2 decimals for simplicity. Take the log of this. So you have my 0.08 log of 8 minus 1.09691. So like that you have taken for all 10 days. They add up and it is minus 2.04081. That is the sum of all increases from January 1 for the 9 days. So what is the average increase per day? So if you take arithmetic mean of log increase, if you take, it is minus 2.04081 divided by increase for 9 days from January 1, it is average is minus 0.2268. The geometric mean is the antilog of it, or 10 to the power minus 0.2268, which translates into 0.5933. So, monthly average, the daily increase of COVID cases from January 1 to 10 in the country seems to be about 0.6%. See, now if you had used arithmetic mean, it would have been 0.95%. See the difference, how much it is. Arithmetic mean appears to be very high increase average per day as compared to the 0.6 we got from using the geometric mean. So, now we will talk about what are the advantages and disadvantages of the geometric mean. It is used more in microbiological, serological research or even calculation of growth, etc. This is very useful because they are all positive numbers, non-negative. The range is very high. So, and because the range is high, the distribution is likely to be widely varying and skewed, which can be helpfully, analyzed by using geometric mean. Because as I said, the transformation or log transformation reduces the skewness in the data. So you get a more stable estimates which are easily translatable for further work and interpretations. What is important in geometric mean is it gives more importance, relatively more importance to smaller values. That's how geometric mean tends to be lower than the arithmetic mean. And because you're working on logs, it is not affected by sampling fluctuations. So sample to sample variation will be less compared to arithmetic mean. But one limitation is you cannot obtain a geometric mean if one observation is 0 or a negative one, because you cannot define the log values of such observations. Now, third mean that we are going to discuss is harmonic mean. And this type of mean, a harmonic mean, is when the data is of rates, speed, acceleration, or data is of ratios, you want to calculate an average, this harmonic mean is the appropriate one. This is the most often used in financial field, in the field of finance and all, for the price to earning ratio, PE ratio is a most common one if you are to calculate what is your where shares, evaluate to what is your average share PE ratio type things. This harmonic mean is very useful. It is defined as the reciprocal of the arithmetic mean of the reciprocals of the observations. So if you have an observation, first calculate everything, the inverse 1 by x1, 1 by x2, 1 by xn. So you add up, and this n, the number of observations divided by the sum of these. If you have, let's say, a simple numerical example, you have three numbers 1, 4 and 4. Harmonic mean is 3 because your observations n is 3 divided by 1 by 1 plus 1 by 4 plus 1 by 4, which is 1 plus 0.25 or 3 by 1.5 is the harmonic mean is 2. More often, harmonic mean is explained through an example of speed calculation, average speed calculation. So we will follow that also. So if you drive a distance d of 120 kilometers at a speed of, let's say, 60 kilometers, which we call it x, and return the same distance at a speed of y or 30 kilometers per hour, what is the average speed? Average speed for the entire journey is total distance travelled by the total time taken. So total distance travelled is 120 plus 120, which is equal to 240. Time taken for onward journey is 120 at 60 kilometers per hour, so 2 hours. And for the return journey, 120 kilometers at the rate of 30 kilometers per hour, so it is 4 hours. So total distance travelled 240 divided by total time taken 6 hours, which is the harmonic mean is 40 kilometers per hour. If you had taken an arithmetic mean of the speeds, it would have been 45, which is not appropriate. Okay, so let me repeat, harmonic mean 40 is not the arithmetic mean as 45 we got it. So if you draw for this certain amount of time at a speed x, and then for the same amount of time another speed at another speed y, the average speed is the arithmetic mean, because the time component is same both legs of the journey. So let me say it again. If you drove a certain amount of time at a speed x, and then for the same amount of time at speed y, then the average speed is the average of x and y. The same principle applies to more than two segments. If you drive a car for 1 hour at 50 kilometers, another 1 hour at 40, and another at 90, the average speed is our arithmetic mean of 50, 40, and 90. That's equal to, say, 60 kilometers. If you drive a series of subtrips at different speeds, and each subtrip covers the same distance, then the average speed is the harmonic mean of all the subtrips. But if each subtrip takes the same amount of time, then the average speed is, as we saw in the previous example, is the arithmetic mean of all the subtrip speeds. If in neither the case, that when you drive different segments at different speeds, then a weighted harmonic mean or a weighted arithmetic mean is the one that is. Let's take a harmonic mean calculation example for a group data. You have class interval, again 10 to 14, 15 to 19, 20 to 24. Total, you have 74 observations. 10 to 14, there are 10 individuals or observations. 15 to 19, there are 14. And then the midpoint, as we discussed earlier, is 10 to 14 is 12.5, 17.5. Here, we are calculating for the arithmetic mean f into x we did. Here, in harmonic mean, we take f by x. So 10 by 12.5 is 0.8, 14 by 17.5, 0.8. Like that, you calculate and take the sum 3.5126. Then harmonic mean is n upon summation f over x, that is 74 divided by 3.5126 is 21.07. This is how you calculate harmonic mean for a group. What are the advantages and disadvantages of this harmonic mean? Again, it considers all observations, it considers all actual magnitude of each observation. So these are two plus points. Again, like geometric mean, it gives relatively more importance to the smaller values. So whenever you want to give importance to the smaller values, you need to consider either a geometric mean or a harmonic mean. Again, it is not affected by sampling fluctuations just as geometric mean, and it can be calculated if the data has negative values, but cannot be calculated if a value is 0, because 1 upon 0 is infinity or undefined. HM is not amenable for further mathematical treatment. We don't know the distribution, how it behaves, type of things. So now, having discussed arithmetic mean, geometric mean and harmonic mean, it makes sense to discuss what is the relation among these three. So if the data set has at least one value different from the rest, what we are saying, if all observations are not same in a sample, harmonic mean is always the least. Arithmetic mean is always the largest or greatest, and geometric mean is always in between. So you want to remember the sequence in the alphabetical order. A, arithmetic mean, is greater than G, geometric mean is greater than harmonic mean. So A is greater than G is greater than H. So if all data values in the data set are same, then all three means are equal. You can just see if the data set has 2, 2, 2, 3 observations, arithmetic mean is 2, geometric mean is 2 into 2 into 2, that is 8. cubed root, that is 2, and harmonic mean, again you can see 3 divided by 1, 1.5, that is again 2. So this is how the relation between AM, GM and HM are kept. So thank you and good luck.